we have this frame of mind that the RAM is just a fancy notebook, right? In which I can write stuff in a binary fashion because we are dealing with electricity and with binary entities, namely transistors, that here are just light bulbs. Now let's make a simple example. As you can see here, I have a little main program that is gonna declare a variable NB and assign the value 42. So what is happening here with this code? Very simply, I'm going to write somewhere in memory, in my RAM, this number 42. So I'm gonna turn on and off the bits accordingly. For the number 42, I have 10, 10, 10, as you can see here from the least significant byte, okay? So I have, long story short, 4 bytes, depending on the machine, but generally speaking, it's 4 bytes. Allocated, and I have the value 101010, which is inside these 4 bytes. NB is gonna be the tag for us, for humans, for programmers, but from a computer standpoint, we have only addresses, of course. So TLDR, we have somewhere in my memory some bits which are turned on and off. Now let's watch again this little program from a stack perspective. Because you know, right, when I have a process, I have my operating system that is giving me a space in memory, the process memory layout, and all the action is going to happen inside the stack, the heap, the data, and the text, and all the segments that I showed you in the previous video. So the stack discipline, namely the allocation and deallocation of all the functions inside my process, happens inside the stack, of course. So here I have the allocation of my main. Inside my main, I have the creation of this variable NB. So I have a local variable, which is inside the function frame of the main function. A function frame, in this case, the main function frame, is the specific space relegated to the main function. So the main function has this specific frame to perform its stuff. So inside this function frame, I have the creation of my variable NB. Okay, let's zoom in a little bit so we can understand better. Here I have my stack. And inside my stack, I have this frame in which my main function lives. And inside this frame, I have some bits which are turned on and off. So that somewhere in memory is the space given by the operating system where the process can do its own business. Of course, now we are inside the main function frame because we are inside that function. Now, you see that the variable NB has a specific address, right? I want to stress out that this is not the real deal. This is not the real address, physical address. This is not what you find inside your real RAM. Indeed, this is a virtual address. Basically, we have the operating system, which is a juggler, is a magician, is doing all the tricks to optimize performance. As long as we are concerned, we don't really care. For us, programmers, this is the address of the variable. Then we have some other pieces like the memory management unit that are going to make all the necessary computations to match virtual and physical address, but we don't care. We don't care. We work on a higher level of abstraction. Our process really thinks that has unlimited memory thanks to this magic of the operating system. But let me repeat to you, we don't care by now. We want to stick with principles. So an address is an address. Now let's watch together a little program so we can really observe the stack discipline and what is going on inside the stack. So here I have a stupid program made up of a few functions. So I declare in my main the variable NB, like before, you just saw, right? So our program starts, of course, from the queen function main. It's gonna declare and assign the value 42 to the variable NB. So we have 4 bytes in memory that contain the value 42, 101010 in binary. And then we reach the point of change value. So we have a function call. Change value is a function that essentially tries to change the value of the variable. Let's see what happens here. So once we reach change value, we stop the execution of the main and we allocate space for the change value function. As you can see, the stack has grown and now we have this new allocation. The stack counterintuitively grows from top to bottom for historical reasons, but this is indeed a growth. So we have the main function that is stopping, and now we are playing the change value function. What is happening here? We have this function that is taking as an input NB, okay, so our variable inside main, and is trying allegedly to change the value of NB to another value, which is 1337, okay? What do you think? Is gonna work, this little program? Can the function change value indeed change the value of NB? Well, let's try. So we have the execution of NB equal 1337, and then we have the deallocation, of course, of the function, because we have finished. A function finishes when we reach the final closing curly brace. Cool, now we are back to the main. We can play again the function. And now we have the call to the printf function. The printf function, you know very well, has to print the value of NB. So we call the printf, boom, we have the allocation. But now, as you can see, the printf is printing 42 again. So my change value function hasn't worked. Or is it? Namely, the function worked, but maybe I didn't quite understand what was going on, right? So what is the issue here? What is the problem? Let's try to understand and deconstruct this issue. So now we stop at the moment in which we were calling the change value function. So I have my main function frame, and then I have my change value function frame, as you can see. So I have my variable NB, both in main and in change value. But let's watch more carefully what is going on here. So I have my frames, right? My main function frame and my change value function frame inside the stack. As you can see, I have NB both in main, right? And then I have also NB, which is in my change value function frame, right? So immediately, what can I understand? Well, I have two variables. They have the same value, the same name, but they are different. They are in different spots, in different places in memory. So NB in main is a different variable respective to NB, which is in change value. And this is tricky, right? Same name, same value, they are the same. Nope, it is not the case. The thing is that when we call some functions, the arguments are passed by value, as we say in C. Passed by value is a fancy way of saying, well, the variable is going to be copied. So what is really changing, change value, is a copy of the variable. It is not the variable which is in main, you see? And if you watch carefully, we have the addresses which are different. They are pretty close because they both live inside the stack, and one function is just calling one another, so they are very, very close, but nonetheless, they have different addresses. That's the main idea. And to make it clear, NB in change value, the argument name NB could have been different, like for example, foo_baz. We don't really care because they are different things. So what is happening here? When I change value NB 1337, what is really happening? Well, the function is changing the value of its own copy. It is not changing the value of NB, which is in the main function. You see? That's the catch. So let's watch what is really happening. We have our variable in change value that, boom, is changing its value. As you can see, I've changed the binary configuration. Now this binary state is representing the value 1337. But then what is going to happen? Well, we have the deallocation of the function change value. So boom. And in the main function, I call again the printf, but the printf is getting the old 42, right? Because I've changed the value which was in another stack frame. So nothing really changed. So printf simply keep using the usual NB42, and the printf is not aware that we don't understand pointers, my friend. So what can we do if I want to change NB which lives inside the main function frame? What is the trick here? Well, my friend, that's where pointers come handy. You see? Let's rewatch again the animation. I have my main function. Inside the main function, I have the variable NB. Then instead of calling change value with NB, I'm doing something different. I'm using the ampersand operator. This ampersand operator is giving the address of the variable to the called function, in this case, change value. So I have to change also the change value, because this time we are getting different kind of inputs. Look carefully, change value is taking this time a pointer to NB. We use the asterisk operator, and as well, NB equal 1337. We have to change a little bit. We have to say at NB. So I'm gonna dereference. This indeed is the dereference operator. We will see later. So this time, the input, the data type that change value is taking is not anymore a variable, but is a pointer. It's this big boy here. He is 8 bytes, generally speaking, but depending on the machine, that is able to point indeed somewhere. So this variable contains the address of another variable. And if you watch carefully, you see the binary configuration of this variable, which is exactly the address of NB. So this pointer is a special kind of data that is able to point somewhere in my memory. We can make indeed reference to something which is not here, not in my local frame, not in my local function frame. Indeed, when we say dereference, we are meaning reference to something which is not here, which is far. Think about the word, I don't know, deportation. Bring someone far. That's the idea. Here we're making reference to something far, dereference. And when I say star NB, I'm saying, hey, go in the address pointed by NB and put there the value 1337. Okay, so we have this condition this time. Let's watch the stack frames. As you can see, I have NB and both NB. So I have my main function frame and then I have my change value function frame. But this time, thanks to NB, what I'm gonna do, I'm gonna dereference this pointer, boom. So I can access the NB, which is in the main function. And then I just do at NB, I can read in this fashion, asterisk NB, is equal to 1337. Now, look carefully what is going to happen. Boom, I'm gonna change the value there, okay? So thanks to the magic of pointers, I'm able to go somewhere else and change values. This, my friend, is called passing a value by reference. Not by value, but by reference. So we give to the function a specific address, a specific place to watch if we want to do its business. So pass by reference, which is very different from passing an argument by value, right? You just saw. So we have the change value function that gets deallocated when we reach the final curly brace, and then we call again the printf. This time the printf is getting as an input NB, which has been changed. You see, I have 1337. So everything works. Thanks to the power of pointers, thanks to the power of dereferencing, making reference to something which is not in my stack frame. And we're ready to rumble. You have the tools to understand everything about pointers, okay, my friend? So here, my friend, I have the actual code. As you can see, my main function in which I declare my variable NB equal 42, and then I call my change value. The function you just saw. I call my change function. Here I call the variable foo bar just to stress out that this is gonna be different. This is gonna be a copy of NB. And you just saw that this program doesn't work. Let's try out. So I'm gonna run my program and I get 42, as you can see. R is just a function that I created. It's just compiling, doing all the checks and so forth. It is like GCC and then launching a.out. It's the same. So we watch again the code, and this time we're gonna tweak a little bit. First of all, I'm gonna tweak the prototype. So the function is taking an address as an input, so I have to use the star. I will explain later why here I don't have the ampersand, because this is a little tricky. The syntax of pointers is kind of tricky, I will explain. So here I have a pointer. Here I give as an input an address. So ampersand NB, I'm giving the address of NB. And here, again, I have to use a pointer here. And here I have to dereference. The difficult part, in my opinion, is that declaration and dereferencing are the same, right? We have the same syntax. This is tricky, but no, not really. I will explain to you. Now we're gonna run again this program. So I'm gonna run, and you can see this time I have 1337. It works. Now let's watch again the classical example of using pointers, and this is the swap function, right? I have two variables in my main, which are 42 and 1337. I'm gonna print their values, then I call the swap, and then I'm gonna print again. As you can see, the swap, the reference to the two variables, ampersand A, ampersand B. So my swap is receiving the addresses of A and B. As you can see from the signature of the function, right? I have as an input two pointers, pointer N and pointer N1. Then I do my swap routine, which is just making a temporary variable in which I can stock the value of N. Then I say at N is equal to at N1. Basically, this is a stupid swap algorithm. So let's try to launch this. And you can see that it works perfectly. So you understand super well by now what is going on, right? With these pointers. So now the tricky part. Declaration and the reference have the same syntax. Why doesn't C have a better syntax for doing this? Namely, a different syntax for dereferencing and respectively another different syntax for declaring. This is confusing. Initially, it was for me a little confusing. Keep in mind this principle. I have that declaration tells me how to use. What does it mean? Well, let's try to understand together. I have here a declaration of a variable, int n, right? A classic declaration. Here, I read in this fashion. To get an integer, just use n. That's what I read, given this declaration. Let's try another. Int star n. What is written there? Well, it is written that I have a pointer to an integer. So I read, as a programmer, to get an integer, just the reference n. You're starting to understand, I guess, right? Here I have n3, which is an array of 3 integers. But here I read in this fashion. To get an integer, you have to index inside this array a value. So in an expression, n square bracket 0, 1, 2 is gonna yield an integer. The last example is a function. For example, here I have a prototype foo int n float n1. What do I read? Well, I read that to get an integer, just call foo with the related inputs. So TLDR, the notation of a variable declaration is telling me what you must do to something to get something of that specific data type. Let's apply this principle to pointers. Here I have a declaration of different pointers, and you can see I have int n, this is just a variable, then I have star pn, and then I have star star pn. What do I read here? Well, I read to get an integer, use n, use the identifier, the variable identifier n, or you can use star pn, or you can use star star pn. They all will yield an integer type when used in this way, in an expression. So in my view, in my mind, a declaration is an how to use, okay, to get a specific data. So here, as you can see, I have many different declarations for different declarations. So I declare here a pointer, a double level pointer, and a 3-level pointer. Okay, here, given the principle I just told you, I see that I have to use this identifier, variable name, call as you want, to get an integer. Here I have to use star pn to get an integer, and so forth, right? Here I have to use 3 times the start on this ppn to get an integer. So if I want to get, for example, an integer from this, what shall I do? Well, I have to use 2 times the, let's delete this and let's do that. Printf, %d, new line. I have to do to this boy here a triple the reference, pam, pam, pam. So a triple the reference, ppn, like that. And this is gonna yield an integer because here is written, if you triple the reference, this boy, you get an integer. If you single the reference, this boy, you get a double pointer to integer. You see, you get the catch. Let's try if it works. So I run the code, and as you can see, I get 42. I get the number 42, perfect. Because I triple the referenced this. Now, if I do something like that, I do p, the stand for pointer, is equal to p, another pointer. So what do? I double dereference this. Why I double dereference? Well, because if I double dereference this boy, I get a pointer to an integer. And here I use pn, which is what? A pointer to an integer. So I'm gonna use directly with no dereferencing, because this, if I use this, I get a pointer to an integer. I'm not dereferencing. You see the catch, my friend. Let's watch if it works. Okay, here I have some controls that I made, so I'm gonna do like that. GCC and then launch. Boom. As you can see, they are equal. They are the same, right? So just keep in mind what I told you. This is an instruction manual. It's telling you how to use this PPP on to get a specific data type. If you do a triple dereference, you get an int. If you do a single, you get a double pointer. And if you do a double dereference of this, you get a pointer to an integer. You just saw here. That's the idea. Okay, my friend. So I guess these declarations are not going to be difficult anymore. Now, another question. Which are the advantages of passing pointers as arguments compared to passing by value? This is a good question, right? Let's watch some pros and cons. Of course, everything in computer science, like in life, has some pros and cons. So we start by passing by value. Of course, passing variable by values, I recall to you that they're just copies. It's easy to understand, right? It's super easy. You pass a variable and the other function is doing its business to that variable, to that copy, and I have nothing to do reference. Super simple. Of course, this is safe because passing only copies is going to prevent some other functions to change value somewhere else and making the code overall unreadable. And yeah, you are sure that the called function is not going to mess up your variables in your local frame. The bad part is that we have some performance overhead, of course. When I pass an object by value, this object has to be copied. So keep in mind, if the object is very, very big, you have a very big memory overhead. Now, we cannot really pass arrays by value. They're not copied because we have a phenomenon which is the array decay into a pointer. I will explain later the relationship between pointers and arrays. But if you have a struct, for example, a struct has to be copied. So you have every time to every function to copy this big boy. You can very easily understand that this is a big overhead. So another negative part of passing by values is the short reach, right? You cannot do what with pointers you can. So this can be good, of course, because you have safety, but can be also bad because you're tied to your local frame. So this can be a plus or a minus. Passing by reference is efficient. So you can pass big data structures, for example, a big struct, and you're going to pass only a reference. So in the call function, you don't have to copy everything. Another plus is that you have direct access to other places in memory. You just saw with the swap function that we can go to change stuff in other places. And this is useful if you know what you're doing. And yeah, this is a way to return, quote unquote, return multiple values, because with a function, you're tied to return only one value, right? You have return the value. Here, we are able to change stuff in other places. So we can make functions that have a lot of functionality. Side effects, of course, is the one I just told you before, is that you can mess up a lot of your code. You can create code which is impossible to read because you have many functions that are changing parts of other code. And overall, it can be a big overhead to have many pointers if you write bad code. And of course, this is complex. Taming pointers is indeed very complex in C. This is one of the most difficult, if not the most difficult, argument related to C programming. So now, my friend, we are going to a website which is very, very useful, especially if you want to learn pointers, because this is a visual tool that allows you to visualize directly pointer. You just type CTutor on Google and you go into this website. Then you just pass some code. Like, for example, here I have this sample code that now we're going to check together. So let's watch in the terminal. So we have colors. I have created a little struct, which is fatboy. It contains a big array of 50 elements, so not that big. And here I declare one instance of an object, right? So I have my fatboy. Then I just put somewhere randomly in my array the value 42. And then I need just to find this 42 in my fatboy, okay? So I call the function find42, passing as an argument fatboy. You see? So I have my find42 that is taking what? Well, it's taking a copy of fatboy, you see? It's not taking a reference. These are passing by value. And then I have a simple routine that is searching the position of 42. So it's searching where in my fatboy 42 is, okay? Now let's watch here the execution in CTutor. As you can see, I have this big boy here, fatboy. That is a big array, you see, a big struct. And when I call find42, I have a copy of this. So I need to pass the entire copy. And this is bad, right? Just keep in mind that you can have many, many functions. This, of course, is going to impair performance, because if you have to copy every time all the thing, it's going to take time, even though computers are really fast. Now let's tweak a little bit the code. I'm going to change this. So I'm going to use %fatboy here, as you can see. So I give an address to the struct, and here in my find42, I'm taking a pointer. So here, now I have to tweak a little bit, even here the code. I need to use this special operator. This is for struct, but this is not important now. And here we are. Now I just use a loop inside equals 0, I minor than size array, plus I. I'm gonna do fatboy v in position I is equal to I, okay? This is just a simple loop to put some values inside all the cells. So let's run it. Here, as you can see, I have some random values. Then I call the find42, giving as an input the address. And then I call the function, boom. Now look carefully. This time you see I don't have the copy. I just have a pointer. I have a pointer to my big array. So my find42 here, my function, doesn't really need to have an entire copy. It just have a reference. So my find42 can make a reference to a variable which is not in its frame. It's somewhere else. It's in another place. Indeed, it's in the main function frame, you see. Here with this website, you can clearly see the stack and the heap. So here are the functions allocated in the stack. So it's gonna do its algorithm in its own frame, looping inside the variable which is in the main. At a certain point, it's gonna find 42 in position 14, which is this one. Of course, this is a star, just randomly. 42 is also a star, because if you watch the ASCII code, you will see that 42 is indeed a star. And my friend, you understood why passing a value by reference can be more efficient. Well, you don't have to copy all the stuff all the time, okay? These, of course, make more sense once you have big structures. For example, fat boy here, which is a big structure, relatively big. Other question, why pointers to different data types have the same size? This is a good question, right? Now, I'm gonna propose to you a little parallel, which is illuminating in my opinion. So if you want to search the address of, I don't know, the Empire State Building, or if you want to search the address of a random dude selling hot dogs at Central Park, are you gonna get a bigger address if you want to go in the Empire State Building, given that this is much, much bigger than the selling hot dog cars? Well, of course, no, my friend. An address is just an address. This is something that is telling where something is. It doesn't hold that the object pointed by this address is big or not. This is not the point of an address. So this is the idea of pointers. If we are pointing something in memory, that can be, for example, an integer, 4 bytes, generally speaking, depending on the system. We have an address of 8 bytes in my machine. If we want to point to, I don't know, a short, we still have a pointer of 8 bytes. If I want to point to, I don't know, a double, which is pretty big, it's 8 bytes as well in my machine, I still have the same pointer. I still have the same size of my pointer. You get the point? Because all the data have an address which is of a specific size. So keep in mind this parallel that I made with the Empire State Building and selling old dog dude cars. That's the same idea, okay? That's the same principle. So here, my friend, I have a little program that is showing you this. I have a char, a short, an int, a double, and then I have a type big, which is just a struct that contains a big array. Here I have 3, 6, 1 million integers, so I have 4 megabytes, okay? And here I simply print the size of, this is an operator that is giving me back how many bytes something is big, of the address of C, of CH, of I, D, and big. So the address of our pointer to these objects here. All right, let's try to launch this code. I have 8, which is the size of the pointer to every data type. To a char, which is the smallest, to big struct, which is the biggest. I have all the times 8. Now, another question. Given pointers have all the same size, we just saw that, why do I need to specify the pointer type? This is another good question, right? Indeed, when I declare a variable, I'm telling the compiler, hey dude, I want an integer, so give me in my machine 4 bytes, or I want a long, give me 8 bytes, or I want a char, give me 1 byte. They are all integers at the end of the day. They are stored in memory as an integer. So here I'm just saying, hey, I want 8 bytes or I want 1 byte of the integer type. I can do the same line of reasoning with floats, but you got the point, right? So the type is telling us even how big an object is. Of course, this is a simplification. At the end of the day, it's the compiler that is deciding how big an object has to be. But anyway, just linger on the principle. You decide the data type depending on the size. For example, if I want a very little number that is ranging from, I don't know, from 0 to 100, I can use a char. I can use a char as a 1 byte integer, not only for chars. This is an integer of 1 byte. So I can really use it for a little number if I want to use. So I can very surgically, with data types, decide how much memory I want to use. And this is pretty useful, right? When you want to have super control of what is going on. Indeed, the C programming language is giving you superpowers in this domain. On the contrary, you have pointers that have all the same size. So what is the point of telling me, okay, this is a pointer to an integer rather than a pointer to a char? So here I want to repeat to you again this point that the binary configuration of 42 is very, very different from the binary configuration of 42.0 float, right? Because we have a different encoding of the binary. We have exponents bits in the real data types. On the contrary, on the integer data type, we don't have this kind of encoding. We have simply the number in a choose complement fashion. So keep in mind this, because we're gonna do a little trick related to this idea. So now I have a little program that we're gonna check to understand why a pointer has a specific type. I have a declaration of a variable, which is an integer, int nb, and then I have a declaration of a pointer. You can see int star ptr. This means that if you dereference ptr, you get an integer. nb gets the value 42, and ptr gets the address of nb. Then I call my printf. So I want to print the value pointed by ptr, and then I do something peculiar, which is this casting. Okay, I'm gonna cast ptr to a float pointer. What is this casting thing? Well, the best analogy that came to my mind is like the real casting, when we want to decide which actors have to play in our film, right? Well, that's basically the same idea. When we do a cast, we are assigning a role to a pointer in this case. So we are assigning the role of a pointer to a float, to my pointer. So here I'm telling to ptr, hey dude, I know that you are a pointer to an integer, but in this time you're gonna play the role of a pointer to a float. So we're gonna do another chuck, and we're gonna dereference again the pointer, but this time of a type float. So here you come, my friend. This is the actual program. As you can see, I have the thing you just saw in the slide. The only thing is that here I have an E because I want to see in scientific notation, otherwise the number is going to be too little. But we can also do like that, 0.60f. Okay, let's try to launch the program. So I'm going to launch. Look what happens. I have this 42, and then I have this 0, 0, 0, 0, 0, and then I have this value. What is that value, my friend? So you just go on this website, which is float exposed, in which you can play with floating numbers. So now let's try to do something. I write 42 here in binary, of course, which is 101010, of course, starting from the least significant byte, which is this one. So I have 101010. Do you see something that you just saw? 58854. What do you see here? 58854. 53550. 53550. So you see what's happening here, my friend. Here with this cast, I'm telling, hey, pointer, when you're gonna be the reference, read those binaries as a float, not anymore as an integer. So you're pointing to a float now, you see? So that 101010 is dereferenced in this fashion. It doesn't see anymore 42, but it sees this very little number, which is this 5 elevated to minus 44. Here we can do in scientific notation, essentially like I did before, like that. And you will see the exact same value. Just you don't see all these zeros, right? 5885454. Of course, here you see a 4 because we have the value rounded. And then elevated to minus 44. That's why you have all these zeros here. But anyway, you get the point. The pointer type tells the compiler how to interpret the binary, the spot in memory that is pointing to. So that's why we have a data type for a pointer. This is crucial all the times you want to get a specific value. Let's play a little bit with this code so we can have a super good understanding of what is going on. This time I'm gonna do a char, for example. I'm gonna cast to a char, and here I'm gonna write directly in binary. We can do that in C. We do 1 and 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And here I write C. What is going to happen in your opinion? Let's close. Let's run. Okay. I cannot do because it's a binary instance, but I can. These are just controls flags that I put. Okay, I launch. I get the value 256, but I don't see any char. Why is that? Well, because when I dereference this pointer, what I'm gonna see is only the least significant byte. A char is 1 byte, right? So when I dereference, I get a 0, the null char. So that's why I don't see anything. Here, if it was, I don't know, a short, and here I just put D. So you are gonna see 256 as well, because when I dereference this pointer, this is gonna see this second byte, if you want, because a short is 2 bytes. Depending on the data type, we are gonna read the bytes pointed by the pointer differently. This is not the full story of the data type of pointers. Indeed, we have C that is very consistent and regular in its approach to address arithmetic. Its integration of pointers, arrays, and address arithmetic is one of the strengths of the language. You will see later that there is a big integration related to arrays and pointers, making it really tricky to differentiate between arrays and pointers. You will see. But keep in mind that here is written, we want pointer arithmetic to be equal to index addressing of arrays. So let's make a stupid example. Don't pay attention to the binary configuration of the RAM. This is just random. I want just to make a point here about pointer arithmetic. So I have my pointer pointing to a char, a pointer to char, and then I'm going to print every time the value of this pointer, namely the address, doing some arithmetic. As you can see, initially I want to print PC, pointer to char, its value. So I'm going to print that. Then I'm going to do PC plus 1, boom. So as you can see, I advanced the pointer by 1. Now the pointer is pointing 1 position more. Then I do pointer C plus 2, so I advance another position, and then pointer C plus 3, I advance another position. Now we say, well, that's easy, right? I have the pointer that is indeed advancing 1 position, but this is just a case. The case is that a char is big 1 byte, so that's why we are advancing 1 byte at a time. I want you to pay attention to the fact that a pointer is just a variable. As you can see, the binary configuration of the pointer is changing as I do pointer arithmetic, because this is just a value that can change. Okay, so the formula to make pointer arithmetic is this one. I have the pointer plus n per size of type pointed. So that's why it's important to know the type of the object pointed. This time I have a char, so it's easy. And let's say is 3, the size of char is 1, so I have the address plus 3, okay? Now let's watch another case. This time I'm pointing to another data type, which is a short, for example. We're gonna change a little bit the code, we're gonna change the value. And now what is going to happen this time when I add 1 to PC? So look carefully, I have this, boom. I have the advancement of 2 bytes and not only 1. Why is that? Well, you understood, because a short is 2 bytes. So when I say PC plus 2, I get, boom, an advancement of other 2 bytes. So 4 bytes respective to PC. So that's what is going on, my friend. You understand super well that the data type is important also when we do pointer arithmetic, you see? So this is gonna discipline how pointer arithmetic is going to work. And you will see that this maintains a highly consistent parallel between pointer arithmetic and array indexes. Indeed, it's like I'm taking the object at position X. So this is just a code that you saw. We are going to start, for example, with an integer this time. I have a pointer to an integer, and we're going to perform arithmetic with an integer pointer. I'm going to compile and then launch. As you can see, we have an advancement of what? Of 4, right? 0, 4, 8, okay? Why is that? Well, you understand super well now, because an integer is a 4-byte entity. If you do your short, like in the slide, so we change here to short, what is going to happen? Well, you already know, I'm going to launch. I have an advancement which is from 2 to 2, 0, 2, and 4. That's all there is, my friend. Other question, void pointers are confusing. Let's dig a little bit. When I say that a pointer is a void pointer, what I'm really saying? Well, I'm not assigning, if you want, a role to my pointer. I still don't know which is the best fit for this specific pointer. So we can say that void is a generic pointer. You should definitely change the word void to generic in your mind. When you see void, just keep in mind that this is a generic pointer. So TLDR, void star, void pointer means we will let you know, right? That's what happens with actors when we don't know which is the best role for them. You can keep this parallel in your mind, it's pretty useful. Now, let's see a practical example. Here I have a stupid program that is going to declare in its main a value, the usual value 42, and then I have a function that is called, which is print data. So this function is able to print that specific data given a specific char, for example, I, F, or C for integer, float, or char. The print data function is taking as an input a void star data. So we have a generic data that we're going to interpret inside the function. So if we have the char I, we're going to interpret the data as an integer, F as a float, char as a char. So you see that inside the print data function, I'm assigning the role to the void generic pointer. Okay, let's watch the code. Okay, here we are. As you can see, I have my integer value here, and then I just print the value. Every time I assigning the role to my generic data pointer. So I'm gonna run the code. And as you can see, I have 42 if this pointer is pointing to an integer. I have the value which you saw before, which is the binary configuration of 42 if it was a float. And then I have the star if it was a char. You understand everything related to this topic, I guess. Now, when in practice we stumble upon these void pointers, well, when you use the malloc function, you see, how many times you have used the malloc, namely requesting at runtime some space in memory. Well, the malloc is returning a chunk of bytes in your memory, but it doesn't really care about the data type. That's up on you. You are going to decide the specific data type, the specific role that the pointer has to play with a casting, right? Every time you use the malloc, you're going to get a void pointer. Now, my friend, given that we are talking about the malloc, I want to show you another little program which can be illuminating about the use of pointers. So here in my main, I have a declaration of a pointer, right, to an integer, and then I assign the value to this pointer, the return value of foo. Foo is a function that is returning a pointer, as you can see here, and essentially is returning a pointer to a variable, which is a local one. Okay? It's returning the address of n, which is a variable inside that. Then what I'm gonna do, I'm gonna use typedef to print the value pointed by the pointer. Okay, what do you think? This program can work? Let's watch out. So I compile, and immediately you see that I have a warning. I have a warning address of stack memory associated with local variable and returned. This is tricky. Then I'll launch, and it works. So I have my 42. But now let's try to change a little bit the code. I'm gonna uncomment this other function, which is bar, and this function very simply is gonna declare a variable and assign a value. That's all there is. What is going to happen in this code? Let's try to launch and then try to deconstruct. So I'm going to compile and launch. I get, first of all, 42, and then I get 1,337. What happened? I mean, here I never changed the value of the pointer, right? It has always been the same. Now, my friend, the issue with this code is very simple. So when I call the function foo, I have the allocation in the stack of this function, right? So my main function is going to stay idle, and then foo is going to perform its stuff. Essentially, it's going to declare this variable 42, and then it's going to return address to that variable. Cool. After that, what is going to happen? Well, I have the foo function that gets deallocated from the stack. So I have a variable which is in a place in the stack which is not allocated anymore, is deallocated. Then I call my printf, I have 42, because that place in memory is not overwritten by other functions. Then what do? I call the bar function, so I have another allocation just above the main, like the foo before. And the bar function this time is declaring another variable. It's declaring this variable here and assigning another value. So the address that is the one of the previous variable n, which was in foo, now is the same address of nb, just by chance, right? Because we know how the stack routine, the stack discipline works. We can, in a hackish way, assign another value to the same address. So that's why in the second printf, if we print from the same address, we get this other value here. So now you understand very well what is going on here. So why the malloc? I'm gonna say int pointer, I declare a pointer to an integer, and here I do n is equal to malloc size of int, okay? And then I say at n, so ID reference this address, I say 42, and then I simply return n. I return a pointer. So this data now lives in the heap, and it's not going to be overridden because in the heap we don't have a heap discipline, we don't have an allocation and the allocation of stuff. So let's watch again the code, and this time I'm gonna get 242s, of course, right? I think that here it's useful to see visually. So we're gonna copy this and paste in ctutor so we can see what happens. So I'm gonna run. I call my function foo. As you can see, I have another stack frame, and then I call my malloc. As you can see, now we live in the heap. We're pointing in 4 bytes which are in the heap. Assign there the value 42, and then I'm gonna return this pointer. As you can see, I have this pointer in the heap that gets returned to the main function. Boom. So now I have a reference to my 42, and when I say print what is inside pn, I'm gonna print 42. When I call the function bar here and I get the variable declaration, I don't have any arrays of previous values like before, right? I hope you understand this point. But now, nothing, because the heap is there, idle, nobody's touching it, and here we go. So the second time you're gonna print again 42. So that's all there is. And this is a thing by which the memory in the heap is useful, because this is memory that is living idle by the stack madness that is happening, allocation and the allocation stuff. Okay, so this is a silly example of the malloc function. Now, if you watch manual malloc, we are gonna see what I used to tell you, that every time we are gonna receive a void pointer from malloc. Then it's up to us to cast it to the specific value we want to have. Okay. Another important thing that you have to keep in mind is that you cannot, of course, dereference a void pointer, for the reasons we just explained, right? What is the role of this pointer? I don't know how to read the bytes pointed because we don't have a type. So look at this example. I have an integer n, and then I have a void pointer in which I assign the address of n. But when I try to dereference it, you see I have a mistake immediately. It's gonna say, hey, I actually don't know which is the data type pointed. How shall I read the bytes pointed? So if we compile, I'm gonna get an error. Argument type void is incomplete, of course. And you understand super well by now what is going on. Now I want to add some more confusion to your life, okay, with these pointers. And this is the question of pointer arithmetic with void pointers. Do you think it's feasible? Well, C standard doesn't allow void pointers arithmetic. Void indeed is a no type, so it's kind of tricky to understand how to handle arithmetic, right? Because you know that arithmetic depends by the size pointed. If I'm pointing to a short, I'm gonna jump 2 bytes by 2 bytes. But it's kind of tricky to get the size of a no type, because void is a no type. Long story short, we can do pointer arithmetic with void pointers. What is going on here, my friend? Well, we have a GNU extension. I can explain better. A GNU extension refers to additional stuff that you can do, additional features you can perform with the language beyond the standard C. In this case, we have an extension which is called pointer arithmetic of void pointers. Long story short, we are gonna treat a void pointer as a pointer to a byte. This makes sense, right? Because when we have a void pointer, we are implying that we have a pointer to a byte. I just have a generic pointer to a byte. So to prove you this pointer arithmetic of void pointers, I have this little program, my usual variable, 42, and then I assign the address of 42 to ptr, which is a void pointer. Then I do some pointer arithmetic. So I'm gonna print the value pointed by the pointer. Here I do a typecast just to make the dereference possible, because I cannot dereference a void pointer. So I'm gonna dereference as an unsigned char. Why is that? Well, because an unsigned char is a byte, if you think about that. And then here the magic. I'm gonna do ptr++. So what? Is it feasible? ptr++? Let's launch the code. Here I'm gonna compile with all the flags that I have. As you can see, I have error because I'm using the flag w error. This is gonna make of every warning an error, but this will work. I have arithmetic on a pointer to void is a GNU extension. Basically, it's telling me, hey, this is something more. This is not the standard C. Now I compile void arithmetic and then I just launch. As you can see, it works. I have just the values that are printed. Let's do, for example, 256. I will get 0100. Let's watch it. 0100. You see? You understand why I got 0100? Because I have only one 1, which is the 9th bit, okay? The 9th bit is the least significant bit of the second byte. I hope you understand this point. So with this GNU extension, it is feasible, but it is not a standard C, so it is not suggested to use. But now you know that you actually can.